What if every movement in the universe, from a falling leaf to the orbit of a satellite, is shaped by invisible fields weaving through space? For centuries, scientists from Faraday in London to Einstein in Bern uncovered how electricity and motion are not separate forces, but part of one deeper interaction that powers modern life. Today, we follow that story. Mattermosaic. Piecing together the universe, one discovery at a time. Today, we explore the story of electricity, motion, and the fields that connect them. This story is built entirely on evidence collected across centuries. It begins with ancient scholars touching amber, and ends with particle accelerators measuring the behavior of moving charges with extraordinary precision. The first known record of electrical behavior comes from ancient Greece, around 600 BCE. Philosophers in the city of Miletus, particularly Thales, observed that rubbing amber against wool allowed it to attract light objects like straw or small seeds. The term electron originated from the Greek word for amber. These observations were simple, yet they set the earliest foundation for understanding electrical forces. In parallel, ancient Chinese scholars during the Zhou and Han dynasties studied static electricity formed by rubbing various materials. Their records describe crackling and sparks generated through friction. Although they did not identify the underlying mechanism, these texts show that electrostatic behavior was observed independently in different cultural regions. These early accounts did not link electricity to motion or fields. They were descriptions of phenomena without a scientific framework. That framework would not emerge until the 17th and 18th centuries in Europe. Between 1600 and 1700, electricity transformed from curiosity into measurable science. In 1600, English scientist William Gilbert published De Magnete in London. Although the book focused on magnetism, Gilbert identified that rubbing materials produced a different kind of attraction not explained by magnetite. He separated electrical attraction from magnetic attraction, making the first clear distinction between the two forces. By the early 18th century, European laboratories refined instruments for generating and storing charge. In 1745 and 1746, Ewald Georg von Kleist in Pomerania, and Peter van Muschenbroek at the University of Leiden independently invented the Leyden jar. This device allowed charge to be stored and discharged, enabling controlled study of electrical motion. In 1752, Benjamin Franklin conducted experiments in Philadelphia that demonstrated the electrical nature of lightning. Franklin introduced the idea of positive and negative charge and proposed the conservation of charge. His letters and published work spread electrical research across Europe and North America. These developments firmly established electricity as a measurable physical phenomenon. Yet, the relationship between electricity and motion still remained unknown. The turning point arrived in 1820 in Copenhagen. Hans Christian Ørsted, a professor at the University of Copenhagen, observed that a compass needle deflects when placed near a current-carrying wire. Ørsted published his findings in a short report titled Experimenta circa effectum conflictus electrici in acum magneticam. This was the first verified evidence that moving electric charges create magnetic fields. The discovery triggered immediate scientific responses across Europe. Within months, French physicist André-Marie Ampère conducted precise experiments in Paris that quantified the forces between current-carrying wires. Ampère formulated laws describing how electric currents interact and proposed that magnetism arises from circular currents within materials. These laws, verified through experimentation, established that electricity and motion are deeply linked. In 1831, Michael Faraday at the Royal Institution in London discovered electromagnetic induction. He demonstrated that moving a magnet near a coil produces electric current. The relationship also worked in reverse. A changing electric current produced magnetic effects around the wire. Faraday built the first experimental electric generator by rotating a copper disc between the poles of a magnet. This disc generator, known as the Faraday disc, marked the birth of electrical power generation. Faraday's findings were not mathematical. They were visual and experimental, recorded in laboratory notebooks with careful detail. He introduced the concept of lines of force, arguing that fields exist physically in space and mediate the interaction between electricity and motion. The next major transformation occurred between 1861 and 1865 in Scotland. James Clerk Maxwell, working in Aberdeen and later London, developed a mathematical framework that united electricity, magnetism, and motion. Maxwell's equations described how changing electric fields create magnetic fields and how changing magnetic fields create electric fields. This mutual relationship formed electromagnetic waves. In 1864, Maxwell proposed that light itself is an electromagnetic wave that travels through space at a constant speed. This claim was confirmed through experiments by Heinrich Hertz in Karlsruhe, Germany, in 1887 and 1888. Hertz generated and detected radio waves, proving the existence of electromagnetic waves predicted by Maxwell. Maxwell's equations created a new understanding of fields. Fields were not philosophical constructs. They were measurable. They carried energy. They interacted with moving charges, and they traveled across space at finite speeds. By the early 20th century, field theory shaped physics. Albert Einstein's work in 1905 demonstrated that the speed of light, derived from Maxwell's equations, is constant for all observers. His special theory of relativity revealed that electric and magnetic fields are two aspects of one unified electromagnetic field, transformed by motion. According to relativity, whether an observer sees a force as electric or magnetic depends on relative motion. This discovery connected electricity, magnetism, space, and time, and, in the 1920s and 1930s, the development of quantum mechanics introduced the idea that particles possess intrinsic properties like spin. Physicists, including Wolfgang Pauli, Paul Dirac, and Werner Heisenberg, showed that electrons create magnetic fields due to their motion and spin. Their work in Zurich, Cambridge, and Leipzig established quantum field theory as the foundation of modern particle physics. According to established quantum electrodynamics, or QED, electric and magnetic fields arise from the exchange of photons. This theory, developed from the 1940s to the 1960s by Richard Feynman in the United States, Julian Schwinger at Harvard University, and Shinichiro Tomonaga in Japan, remains the most precisely tested theory in physics. Laboratory measurements in modern facilities, including the Large Hadron Collider near Geneva and synchrotron laboratories worldwide, continue to confirm the predictions of field theory with extraordinary precision. These experiments do not speculate. They measure the behavior of moving charges and fields at extremely small scales. Fields do not only exist in laboratories, they shape planetary systems and biological organisms. Earth's magnetic field, generated by the motion of molten iron in the outer core, has been studied through geological samples dating back billions of years. The geomagnetic reversals recorded in volcanic rock across regions like Iceland, Hawaii, and the Mid-Atlantic Ridge verify that field interactions influence the history of the planet. In living organisms, electric potentials guide the motion of ions across cell membranes. The flow of charged particles in neurons, measured since the early 20th century using microelectrodes developed by scientists like Alan Hodgkin and Andrew Huxley, demonstrates that motion and electricity operate in complex biological systems. None of these processes violate established theories. All are consistent with the interaction of fields and moving charges described by classical electromagnetism and quantum physics. The story of electricity and motion is a story of evidence gathered across continents and centuries. It is a scientific narrative that begins with amber in ancient Greece, moves through Faraday's laboratory in London, and reaches modern particle accelerators. The relationship between electricity and motion reveals that fields are not empty abstractions. They are real physical structures that shape matter and energy. To understand how electricity and motion interact is to understand the hidden architecture of the universe. This is Mattermosaic, piecing together the universe one discovery at a time. If this journey through electricity and motion sparked your curiosity, drop a like and share your thoughts below. Subscribe and join us as we explore more forces that shape our world.